I'm going to finish up chapter 12. Again, it's about solids, and we were talking about the different shapes. Here's a diamond. And now remember, we talked about graphite was like sheets. That's where they slide. That's why they're much softer. In a diamond, the carbon is connected to all four, and then it forms like a tetrahedron. So it's really strong. It's really tough. And they always say diamonds are one of the strongest materials, that we have on Earth. So diamond, the only difference between diamond and graphite is basically how it was formed, in the sense of that the diamond has a different network of bonding than graphite does. Okay, the atoms are covalently bonded. They form these regular patterns, and a covalent network solid has a higher melting and boiling point. And again, a diamond this is the strongest of the covalent bonds. Okay, the covalent network solids, I guess I should call them. But they form a tetrahedron instead of like the graphite did with the sheets. Well, they can slide across each other. That's why they're much softer. Okay, so we talked about semiconductors way at the beginning. Those are the metalloids. Okay, there are some other semiconductors that are just pure elements. Okay, you can see silicon, and it's in the shape of a diamond. So silicon is, if it's to be a true diamond, it has to be carbon, but silicon can form a shape because, again, silicon has 4 bonds, so it can do the same thing. We have aluminum phosphate bond. It's called a zinc blend, which is weird because it doesn't have zinc. But that's the bond that it forms, or the structure type that it forms. And you can see we have several of those. But again, these materials over here, these tend to be metalloids. We've got indium and antimony. Tin isn't one, but it's close. The same with aluminum. Aluminum is in the same area. So these elements tend to form semiconductors. And again, remember, semiconductors are great for technology. If it wasn't for semiconductors, we would not be doing this online stuff, because we wouldn't have computers, we wouldn't have cell phones, we wouldn't have, heaven forbid, video games, that kind of stuff. Okay? And again, the ones that have 4 valence electrons are the best. Silicon, germanium, and tin, and then these are your best semiconductors. Okay? So the inorganic semiconductors, germanium, arsenic, they have an average of 4 valence electrons. Germanium and arsenic have 5, but again, they're in that middle range, and they're really good at forming semiconductors. Okay, sometimes what they do to increase the conductivity of semiconductors, they do what they use doping. They change the gap. Okay, you can see here's an N-type and a P-type. What they do is they fill in, they switch them to make the gap different. So part of this is up here and part of this is down here, and so on. This one doesn't have anything as far as, it doesn't switch at all. It's undoped. Here they switch a little bit of each part. Okay, and the N-type is going to be in the top. The P-type is going to be on the bottom. Okay, the N-type semiconductors have more electrons, so the negative charge travels across the band. The P-type have fewer electrons, so they kind of have a hole that they travel through. And again, this gap slows down. Like if you're talking about a computer, you have information coming into it. It needs to be processed, okay? So if you use metals, it would just go too fast. It wouldn't have time. But because we have this gap, now it gets a chance to read that information and tell us what it is. So that's why semiconductors are so important to us, because they slow down the information. They let it go through, but it goes slow enough that you can still understand. The processor can still use it and understand what it's saying. Okay. All right. Another type of solid is called polymers. Polymers are molecules that have very high molecular weight, and it's a bunch of little molecules together. If you do biochemistry, sugars like glycogen, there are a bunch of sugar units put together, or like starch, it's a bunch of. So anytime you take a bunch of smaller units and put them together, the small units are called monomers. The big unit is called a polymer, and that's when you get them all together. Poly meaning many. Okay, plastics are an example of polymetric solids. Okay, you can form into various shapes. They're relatively soft. They're very pliable. Okay, so they're not as super strong because, again, they'll melt easy and that kind of stuff. But we have different types of plastics, and I'm sure you guys have seen the little triangles with a number inside. It tells you that there's 7 different kinds. I think now there might be 8, but they tells you the kind and what they're made out of. and they have different purposes. You know, your pop bottle versus a plastic container. Okay, the thermoplastics, they're melted and reshaped. So those are the good ones. These ones down here. Thermoplastics are the ones that are recycled because again, they can be melted down and reshaped. Okay, they have estomers, which are very rubbery. They stretch and return to their shape unless stretched beyond their limit. So, you know, they can be stretched a little bit, but once you stretch them too far, then they can't. But again, these are types of plastics, and plastics are polymers. Okay, there's two primary types of polymers. There's one called the addition polymers. They're formed when the bond breaks and then you throw something in there. So you're adding something to it, you make new bonds. And then they have condensation ones. That's where a small molecule is removed between two large molecules. Okay, so addition, you're adding electrons in there. Condensation, you're removing. Okay, those are the two different types, the ways they make polymers. And we're talking about specifically for plastics. Okay, here's a bunch of, we have polyethylene, which is used in films, polypropylene used in kitchenware, polystyrene, worst stuff ever. This is, you know, the stuff that your coffee cups, you know, the disposable ones. The thing to remember about polystyrene, you guys, is it never ever breaks down when you throw it away into a landfill. So it's not a good thing to use. They used to, like in fast food restaurants, all their hamburgers, they used to put them in polystyrene until people are like, hey, you know, you're filling up the landfills with that junk. So that's now why they wrap them in paper. Okay. So these are addition ones: polyethylene, polypropylene, polystyrene, PVC. You guys know what PVC pipe is, right? Okay, here's some condensations. Oops, sorry, you guys. Didn't mean to do that. Polyurethane, nylon. Okay, different ones. So you have different ways of making your polymers, and they have different functions. Okay, so if you have polymers, they're bulk properties. Again, they're not straight chain. Okay, the more you add to them, then they start to twist. Okay, and that makes them a little bit stronger. Chains have a variety of lengths and therefore a variety of molecular weights. You can have huge polymers and you can have smaller ones. Again, it depends on what its purpose is. The material can be very flexible. Plastics are very flexible. For a while, they were the bomb until they realized that they never, ever go away. Okay, so when you're talking about plastics, you have crystallinity. Short order can lead to crystallinity. In other words, when you, here's a, if it isn't very long, it can actually start to form crystals. Okay, this makes the polymer much denser, so it's harder. So like your plastics that you have in kitchen utensils and stuff tend to be short order because you want them to be stronger, tougher. Okay, you want them to last. All right, and again, you can enhance it by stretching and pulling when the polymer is molten. In other words, when it's really hot, you can change its shape. Okay, if you want to change a polymer's physical properties, okay, the chemical, you got bonding. Okay, so if you strengthen, if you pull on them, you actually change the bond length, and that can strengthen and stiffen the substance. They have something called vulcanization. You hear that a lot with sulfur. It's how they make rubber. Okay, they use vulcanization so that the chains are cross-linked. They come in contact with each other, so they form cross-links, and then they make them much stronger. And again, vulcanization is used with sulfur when they're making rubber. You can see the bonds here forming. Okay, and again, it's really important because let's face it, we want our tires to be tough, right? They use vulcanization when they make tires. Okay, and then I said there's nanoparticles, which is kind of a really new, well, now it isn't, I guess it's been around for a while, but it has been, where you have particles that are super tiny. They're nanometers. That's why they call it nanoparticles. They're adding nanoparticles to make things stronger. Okay, their properties are studied all over. Like I said, I know that NDSU had a big nano lab. I don't know if they still do. This, you know, this is, I'm talking about 15 years ago. I remember them starting it up. I know UND has nanoparticles as well. They're really a big thing. And what they do is they can add these little particles. They're so tiny, but they can add stuff and they can change things. They can make them better conductors. They can make them stronger. There's all kinds of crazy things you can do with these nanoparticles. And really what a nanoparticle tends to be like little tubes, usually made out of carbon. Okay. Here you can see, oh, the gap energy. Remember, that's the gap that the information travels through. So again, this is used with semiconductors. It's really important to add these nanoparticles to make them stronger and make them better. Okay, so again, 10 to 100 atoms is all. If you think about it, in 1 mole of a substance, you've got Avogadro's number, 6.02 times 10 to the 23rd. So you can imagine how tiny this is. And again, that's why they're called nanoscale. It's really a small, small, small scale. Okay, they have quantum dots. And again, they're semiconductors, really tiny semiconductors that they can add to materials to make them better. Okay, they can use nanoscales. Here you can see if they take metals and they add nanoparticles, they can actually add colors and stuff. When they make stained glass and stuff, they can use nanoparticles. Cool, right? The red gold that you see in stained windows is made from the solution. This had nanoparticles. People did it before and they didn't even realize what they were doing. Okay. There's a new form of carbon found in the mid 1980s, which I know that's 40 years ago, so it doesn't seem, but they call them buckyballs. Have you guys ever heard of those? It's a different arrangement of carbon that they found, and it's super strong. Because again, we're used to carbon as graphite sheets or a diamond where you got the tetrahedral shape. But here they found that the carbons form these little balls. There's 60 carbon molecules here. And they call it the Buckminster fullerene, or they call them buckyballs. Okay, it's the shape of a soccer ball. Okay, and this again, they can do on a small scale and add strength to stuff. Okay, so when you're looking at carbon, like I said, there's certain patterns. Here's your graphite, here's your diamond, and then here's your buckyball. Okay, if you straighten out the buckyball, you can make new particles. And again, they like to make nanotubes. That's the big thing with nanoparticles, at least that I've heard of. Okay, they take nanotubes and they add them to metallic and they make them much better semiconductors, and then they don't have to use the doping where they stretch it out. They're just adding. It's a much simpler process and it's a lot cheaper. Okay, they make them very strong. And then graphene, again, you're taking single layers of graphite, but you're adding these nanoparticles in there. And again, you're making them tougher and stronger. So there's a lot to do with it. I'm not overly sure where the research is right now, but that's kind of stuff that's been going on. Okay, so that is chapter 12. All right, that's all we got. We're done with chapters from this semester.